In this video, we want to continue our discussion of Le Chatelier's principle. Le Chatelier's principle tells us that if a stress is applied to a reaction mixture that is at equilibrium, the net reaction occurs in the direction that relieves the stress. And we can stress or disrupt a reaction that's at equilibrium by changing the concentration of reactants or products. We can change the pressure and volume of our reaction mixture, or we can change the temperature of our reaction mixture that is at equilibrium. In this video, we want to show how changing the concentration of reactants or products disrupts the reaction that is at equilibrium and how that reaction reestablishes equilibrium. So in other words, if a reaction is at equilibrium and the equilibrium is disturbed by changing the concentration of reactants or products, the reaction we know will proceed in the direction in order to restore equilibrium. So our question here is exactly why does this happen? We want to explain how equilibrium is reestablished in terms of concentrations and reaction rates. So that's our goal here today. Explain how equilibrium is reestablished, and we want to explain it in terms of concentrations of reactants and products, and reaction rates of forward and reverse reactions. So let's use our reaction here, the formation of ammonia, in order to help explain how equilibrium is reestablished. So we have this reaction, and let's say it is at equilibrium, and we disturb the equilibrium by increasing the concentration of nitrogen. Okay, so we have our reaction mixture at equilibrium. We disturb it by increasing the concentration of nitrogen. Explain why the net direction of the reaction will be from left to right. So if we increase the concentration of nitrogen, we know that the reaction will proceed from left to right. Our net direction will be from left to right in order to reestablish equilibrium. And we can show that using QC and KC, but we want to explain why that happens in terms of reaction rates and concentrations. When the reaction is at equilibrium, we know that the rates of the forward and the reverse reactions are equal, and the concentrations of our reactants and products are constant at equilibrium. So we know that. So let's show that graphically. Okay. Here's a plot of concentration versus time. Let's say we start with some concentration of our reactants. Over time, the concentration of our reactants will decrease, and the rate of the forward reaction will slow, and the concentration of our product will increase over time until eventually our reaction rates are equal and our concentrations are constant. So here we're just explaining how equilibrium is established. So be sure you review that and be able to explain exactly how you establish equilibrium. So we have this reaction at equilibrium, and we're showing that graphically. Our question though here is, once we have established the equilibrium, what happens when we add the nitrogen? We add some nitrogen, increase the concentration. What happens? How is the equilibrium disturbed? And why is the net direction from left to right in order to reestablish that? In order to explain this, let's break it down into 3 steps or 3 phases. Let's explain what happens immediately after we increase the concentration of nitrogen. And then after some time, after we've increased the concentration of nitrogen, and then ultimately, what happens when equilibrium is reestablished. So we'll explain these in more detail, but you'll see that we're going to break this explanation down into 3 phases or parts. So let's start with phase 1. We have our equilibrium, our reaction at equilibrium, and we increase the concentration of nitrogen. What happens immediately when we do that? Well, first thing we want to say is what happens to the concentration of reactants and the rate of the forward reaction. And let's explain what happens to the concentration of the products and the rate of the reverse reaction. So when we increase the concentration of nitrogen, well, we're increasing the concentration of our product, or excuse me, our reactant. So what's going to happen to the rate of the forward reaction? Well, the rate of the forward reaction will increase. because collision theory tells us if we increase the concentration of either reactant, we're going to have more collisions between the reactants. So we're going to have more frequent collisions, and therefore the rate of the forward reaction will increase. So initially, when we first add that nitrogen, increase the concentration of our nitrogen from our equilibrium mixture, the rate of the forward reaction will we'll get a big increase in that rate because of the more frequent collisions. Well, what about the products? We haven't changed initially. Now, this is immediately after the concentration of ammonia hasn't changed from its equilibrium concentration. So since the concentration of the product has not been altered, the rate of the reverse reaction remains constant. So overall, we have, flip back here, overall, our reverse reaction hasn't changed. The rate of the reverse reaction hasn't changed, but the rate of the forward reaction has increased. So there's a net increase towards from left to right. So let's show that graphically here. What did we do? What did we do? We increased the concentration of our nitrogen, right? Oops, sorry about that. We increased the concentration of our nitrogen. So we had a spike in the concentration of our nitrogen. Our ammonia and our hydrogen, we haven't changed those concentrations. So now, soon after the concentration change, what's happening next? What happens to the concentration of reactants and the forward rate of reaction? And what happens to the concentration of products and the rate of the reverse reaction? Let's explain that. Well, since the rate of the forward reaction, remember we added the nitrogen and we said the rate of the forward reaction increased, the rate of the reverse reaction remained constant because we initially did not change the concentration here. Since the rate of the forward reaction is now greater than the rate of the reverse reaction, the products are being produced faster than the reactants are being produced. So we're having a net increase in the concentration of our product because we're producing product faster than we're producing the reactant. So overall, the concentration of reactants will begin to decrease and the concentration of product will begin to increase, right? It's because our forward reaction rate is greater than the reverse, so we're going to have a net increase in the product and a net decrease in the reactant. So as the concentration of reactants begin to decrease, what's going to happen to the rate of the forward reaction? It's going to begin to slow down. So we got an initial burst or initial increase in the forward reaction rate, but as the concentration of reactants decreases, this rate's going to begin to start to slow. Well, what about the product? The product, we're beginning to increase the concentration, right? And so the concentration of product increases, the rate of the reverse reaction is going to start to increase. Again, collision theory tells us that the concentration is kind of proportional to the reaction rate. So let's show that graphically. Here we had our increase in our nitrogen. We added nitrogen, so we had an immediate increase in our forward reaction rate. What's going to happen to the forward reaction rate over time? It's going to start to decrease, right? So the forward reaction rate is decreasing. You can see it increased and now it's starting to decrease. What about the rate of the reverse reaction? Our concentration of ammonia is going to start to increase. Whoops. Our concentration of ammonia is going to start to increase, and therefore, remember, concentration over time is rate, so the rate of the reverse reaction begins to increase. Well, let's go to the third phase. Equilibrium is reestablished. The rate of the forward reaction continues to decrease, so our products continue to, our reactant concentrations decrease, and so the rate of the forward reaction continues to decrease, and the rate of the reverse reaction continues to increase until these rates are equal. Well, once these rates are equal, we've reestablished equilibrium. So the concentration of reactants and products, again, remain constant, and our reaction is at equilibrium. So let's show that graphically. So let's review what happened. We have our reaction here. It's at equilibrium. Our concentrations are constant and our reaction rates are equal. We add some nitrogen. So we add some nitrogen, so we get a big burst in the concentration of nitrogen. And the overall rate of our forward reaction increases. The rate of the reverse reaction remains constant. So we start producing more product, or excuse me, produce product at a faster rate than the reactant. So the concentration of ammonia begins to increase. The concentration of our reactants begins to decrease. So what happens? Our our concentrations decrease here and here, so our reaction rates begin to slow, and the concentration of our product begins to increase, so the rate of the reverse reaction increases. And this occurs again until our concentrations are constant and our reaction rates are again equal. So again, we've reestablished equilibrium here. So we've shown you here how we can reestablish equilibrium by increasing the concentration of one of our reactants. Be sure that you can take this and apply it if we gave you a different problem. Maybe we decrease the concentration of our reactants. If we decrease the concentration, explain why the reaction would shift from right to left. And we would explain that in terms of reaction rates and concentrations. Or if we increase the concentration of our product, if we increase the concentration of product, the reaction would shift from right to left again in order to reestablish equilibrium. So whatever we have, either we increase or decrease either reactant or product, you want to be sure that you can explain in terms of concentrations and reaction rates how our equilibrium is reestablished. So take some time and be sure you practice those explanations. We've just shown you one example here, but be sure you can apply that to other examples.